Ever wonder what would happen if you could travel near the speed of light? Would time slow down for you while it raced on for everyone else? Welcome to the fascinating world of the twin paradox, a thought experiment that questions our understanding of time itself. Originating from Einstein's theory of relativity, this paradox presents a curious situation where one twin, embarking on a journey close to light speed, ages slower than the other, who stays on Earth. This is due to the effects of time dilation, a mind-bending concept that suggests time can stretch and shrink depending on one's relative velocity or gravitational field. It's as if time has its own elasticity, bending and stretching according to the laws of physics, not man. So, are you ready to dive into the world of the twin paradox, where time isn't exactly what you think it is? Buckle up and let's go! Imagine two identical twins. One decides to take a trip to space, traveling at nearly the speed of light, while the other stays on Earth. What happens next? In this scene, we're simplifying the concept of the twin paradox, a mind-boggling phenomenon in Einstein's theory of relativity. Here's how it goes. The adventurous twin hops into a spaceship and zips off into the cosmos at speeds close to light's pace. Meanwhile, the homebody twin remains grounded on our planet. Now, according to the laws of physics, time moves slower for objects in motion compared to those at rest. This is known as time dilation, a key aspect of special relativity. Simply put, the faster you move, the slower time passes for you relative to a stationary observer. So, our space-traveling twin, zipping through the cosmos, experiences time at a slower rate than his Earth-bound sibling. For him, maybe only a couple of years pass on his epic space journey. However, back on Earth, his twin experiences time at the usual rate. So, while the astronaut twin is off exploring the universe, decades might pass for the twin left behind. When the spacefaring twin finally returns home, he steps out of his spaceship and something extraordinary happens. He finds that his twin brother, who was once his same age, is now an older man. He's essentially traveled into the future. This is the essence of the twin paradox. It's not about biological differences or space diseases causing one twin to age faster. It's about the fundamental nature of time itself, and how it can be stretched and squeezed by the forces of speed and gravity. So, the space-traveling twin comes back younger than his Earth-bound sibling. Sounds like science fiction, doesn't it? But it's not. It's physics. Now that we've grasped the basic concept, let's delve deeper into the key elements of the twin paradox. First up, time dilation. A mind-bending concept that comes straight from Einstein's theory of special relativity. Time dilation describes how time slows down for an object in motion compared to an object at rest. Imagine one twin traveling through space at near light speed, while the other stays on Earth. To the traveling twin, their clock seems to tick normally. However, from the perspective of the Earth-bound twin, the traveling twin's clock is ticking slower. This means that when the traveling twin returns to Earth, they will be younger than their Earth-bound sibling. Crazy, right? Next, we have relative velocity. The faster the traveling twin moves, the more pronounced the time dilation effect becomes. So, if our spacefaring twin were to zip around at, say, 99% the speed of light, they would age significantly slower than their twin on Earth. But remember, from their own perspective, everything seems normal. It's only when they return and compare themselves to their twin that the effects of time dilation become clear. Finally, let's consider gravitational fields. This is where Einstein's theory of general relativity steps in. According to this theory, time runs slower in stronger gravitational fields. So if our traveling twin spends some time near a massive object like a black hole, they would age even slower. These three factors, time dilation, relative velocity, and gravitational fields, all work together to create the age difference between the twins. They're not just theoretical concepts either. They have real-world implications for astronauts, satellite technology, and even your GPS system. So, the twin paradox isn't really a paradox at all. It's a fascinating consequence of Einstein's theory of relativity. The twin paradox isn't merely a theoretical concept. It has real-world implications, and has even been tested experimentally. One of the most compelling pieces of evidence that supports the twin paradox is the Haffel-Keating experiment. Conducted in the early 70s, this experiment involved atomic clocks flown around the world on commercial airliners. When compared to reference atomic clocks at the United States Naval Observatory, the flown clocks showed time dilation effects as predicted by Einstein's theory of special relativity. The traveling clocks were a tad slower, just as the theory predicted. It was an elegant demonstration of the twin paradox beyond the realm of thought experiments and into the tangible world. But the implications of the twin paradox aren't just confined to the esoteric world of physics experiments. They have practical applications in our day-to-day life as well, particularly in the technology we use. Consider the Global Positioning System, or GPS, a technology that many of us use daily. It's a system that relies heavily on the principles of special relativity, including the twin paradox. You see, the GPS system works by using satellites to send signals to receivers on Earth. These satellites move at high speeds and are at a higher gravitational potential compared to the Earth's surface. According to the theory of relativity, this means time will run slower for the satellites compared to the receivers on Earth. If this time dilation effect wasn't accounted for, the GPS system would give inaccurate location data, making it practically useless. So every time you use your GPS to navigate, you're actually using technology that has been designed with the twin paradox in mind. The engineers who designed the system had to account for the time dilation effects predicted by the theory of relativity to ensure the system would work correctly. So the next time you use your GPS, remember, you're making use of the same principles that make the twin paradox possible. We've traveled near the speed of light, explored time dilation, and aged differently than our twin. It's been quite a journey, hasn't it? We've delved into the depths of Einstein's theory of relativity, unraveling the intriguing twin paradox. We've simplified this complex concept and highlighted its salient points, making it palatable for everyone. We've seen how it challenges our intuition, how it impacts astronauts, and how we've found tangible evidence of its existence. We've also touched upon how popular culture has embraced the twin paradox, its role in cosmic phenomena, and even its practical applications in our daily lives with GPS and satellite technology. The twin paradox isn't just an abstract idea, it's a tangible consequence of the special theory of relativity, a fascinating insight into the very fabric of our universe. So next time you look up at the stars, remember that if you could travel there at nearly the speed of light, time would have a different meaning for you. And that's the magic of the twin paradox.